haven't get the homework assignment yet, so I promised to do it this afternoon and maybe give it on Tuesday. Are there any questions about what we covered so far in the project presentation? I'll send an email with logistics. Since time is short, I would like to either upload all the presentation on one account, so people don't have to, take time to switch between the presentations. So either send it to me or put it on the desktop. We'll use it from one account and shoot for 10-minute presentation, about 2 minutes for questions and stuff, right? So, what do you think of this paper? So this is one of the papers on memory systems, memory module, right? In general, was this a easier paper to read? Was it what is there? I hope by this time you sort of kind of get the picture of like how all these things fit in, right? In terms of, I guess you can look at the paper to see if it's very easy to read. They're more recent and sort of harder to read. It's like older. But this is one of the papers from Mark which came about. There are not many papers from Mark in terms of publication or SOSP or other conferences. It had a lot more influence, on the OS field, right? So this is one of the things about Mark, and they kind of articulate why they're different from Accent, which was the other operating system from CMU, right? And I think one of you mentioned in the reviews that one of the nice things about these group of people, not just in this paper, but the papers that we read, the way they influence the field is not necessarily by, of course, they made the Mark publicly available, which is sort of the base for your Apple operating system. But these people went on to join companies like Microsoft. So Microsoft, if you look at the senior VP for research and all those things, Rick Rashid, this is a fairly senior guy. This guy went on to VP of something at Apple for a while. So these people kind of influence through those stuff. So whatever they're talking about here gets into our operating system, not with much fanfare, because you're not going to see Windows Vista argue that we really did this kind of sort of a thing, but it's kind of sort of built in, right? So, was it an easy paper to read? What is your sense of the paper itself? I didn't see anything controversial in the reviews, but did you get what they were trying to say? So, what is the high order bit? What's the major contribution from this paper? Who wants to volunteer? Before I start picking people, right? So, what's the
major contribution for the using the memory, virtual memory to improve the communication between processors, right? Processes, like that. That's something new, but that was something new at that time, But I think it's still a problem right now because the inter-procedure communication is still a bottleneck because the memory thing is too slow.
Is that what everybody else got out of the paper? So what do you think of that paper? What is the paper talking about? You can go.
Use memory mapping and how to deal with second memory is
So I would like one more. So it seems like whatever you guys said was not the same, right? So what about you? Like, what do you think the paper is saying? I want one more opinion. So who wants to volunteer for one more opinion on what is good about this paper? Or you can see the paper sucked, right? Okay. What do you think? Yeah.
This paper introduces the basic idea of the map,
Okay.
The tasks,
Mhm.
the messages, and the threads. Also, because the map is a microkernel, so the interprocess communication is very important for this kernel. So I think that based on this paper, later on many like Duality work has been done.
So I think some of what you guys was similar, right? So do you think this paper is introducing the notion of inter-process communication? Was it their focus on optimizing inter-process communication, or what have you? So how does the Mach inter-process communication work? They actually explain that, right? They explain the notion of ports and messages. So how does the ports and messages work? So who can explain what ports and messages are? Yeah.
So a port is like a queue that is a queue of messages, and then the processes have access to the port, and they can pull messages off the queue and process them. And so then, if two processes want to communicate with each other, then one has to grant access to that port to the other process.
So the way they would, so many of you know socket programming, sockets and network programming. So think of it, sockets as no more complicated than like a file open close, right? So somehow you establish a connection between two machines, and then after that it's write and read, right? So whatever you write on one end, you can read on the other end, right? So that's one communication primitive that is widely used, right? So I can open a communication with another process, and so whatever I write here could be read there, whatever could be read there could be written, vice versa, right? So how is this port mechanism different, or is it the same? Is it that they're calling it differently, but essentially the same, right? So you have two. Let's say you have two tasks, right? And sockets essentially do the same thing, right? I mean, you have some magic trying to figure out how to establish this stuff. But essentially, once you establish this thing, whatever you write here would be read here. Whatever you write here could be read here, right? So this is the socket abstraction. And the port abstraction, are they the same? Are they different? If they're the same, then essentially Mach was, you could implement, I mean, if they're making a claim that ports and messages are somehow different in Mach, right? From our perspective, it's no different, right? We can use sockets or other program abstraction, right? So what does ports provide? What is the stuff with ports that? I think you sort of mentioned a little bit of it, right?
That you have like multiple sender, but only one receiver.
So okay, so you can have one receiver and multiple senders, right? So this is possible in ports, which is not possible in your socket, right? So now you can have multiple senders sending to the same port, right? So that's one difference. What's the other difference?
Do sockets have the idea of having a queue, or is it just kind of you?
They have an idea of queue, right? It's sort of like your read-write buffer. It's not so discussed that much in the socket sense, but that's, any primitive you have to implement has to have some kind of buffering, right? Otherwise you have to block the other end. So that's one thing.
Yeah, don't datagram sockets have multi-sender, single receiver?
Let's assume that they don't, right? The thing is, if you have a UDP kind of socket, then if you don't have a connection, then you don't have to do that. So let's assume connection oriented, right? Actually, you mentioned it, right? The notion of capabilities, right? So in the socket primitives or those kind of things, there's no notion of capabilities. In ports, that's important aspect, right? So what is a capability?
It's the ability of a process to send a message to a port.
So it tells whether this process can actually send something to this stuff, right? So if you have this capability, think of it as a token, right? As long as you have a valid token, you're allowed to communicate with this stuff. So a third process which comes here cannot communicate with this unless it has a capability, right? And in that fundamental way, these things differ because depending on how you do the networking stuff, the system does not enforce who can send to what. I mean, anybody can send to any port as long as they know something exists, right? Whereas here you need to have this capability, and only if you have the capability can you communicate. So if this one does not have capability, this cannot communicate with that, and that's enforced by the kernel, right? So only people who have capability can communicate with you. And how do you get the capability? How do you acquire the capability to
You receive a message from another process that tell you that you can use this port.
Yeah, so you need to have another port which communicates that with you, right? So if you let's take away the sockets now, right? Ports are sort of a one-way thing, right? So you need to have another port here, which this one can communicate, right? So wait a minute. So I need to have another port that this one has, where I can send the capability. It's the other way, right? So I need to have a port open, right, where you can send me the capability which I can use to contact back with you, right? So these are unidirectional for the most part. So if this one wants to communicate with me, I need to have a port here, right? And if I have this port, then I can use an existing port to send you the capability, right? So one of the messages I can send is a capability, right? So the messages in ports have types. So you can actually send a capability and the system understands the capability. So you need to have this mechanism to figure out who can talk to each other. So in that sense, it differs from your networking protocols where anybody can talk to anybody. Like if you're running a web server, anybody can talk to you kind of stuff. Here, I can only talk to people who I control because I need to give the capability somehow. So they have to be somehow linked to me. And the way I send capabilities is through other ports and messages, right? So that's the aspect of MARC, right? So you have this notion of ports and messages, right? For the most part, they look just like any networking protocol stuff. It's reliable, right? And anything you send will be sent on the other end. And you can only send if you have the capability. You have multiple senders to the same receiver, and that's one nice thing. But essentially, that's what it gives, right? So if you want to build a distributed system, you're supposed to use distributed system or the kernel talking to application level server or what have you. You communicate through these messages, ports and messages, right? Is that all you need? Is that all you need for the system to work? Let's assume that there's only two processes which are trying to communicate. Do you only need the communication mechanism, or what happens when the message goes on the other end? So if I make a request here, right, it's called inter-process communication stuff, right? So if this process is sending something to here, what happens? What happens here? You need something to process those requests, right? So even though they call it inter-process communication stuff, the way they're using it is more like a remote procedure call, right? So if I want something done here, if I want to call some function, I send a message over here, and something over here would have to decide that this message is a request for some particular stuff. So it will call that particular function, and when it's done, it'll have to use the remote port to contact back to your stuff, right? So even though the way they build this depends on the ports and messages, but what you really want in the system is the remote procedure call mechanism. So when they talk about it, it's actually a remote procedure call kind of mechanism where I want to get some service from here, I send the message, it goes over here, somebody has to process it, take it, do the service at whatever I've asked for, and then they respond back to the answer for that, right? So if I say I want a particular page, and this happens to be a file store or something, if I say I want this particular block, right? I send this request, the ports and messages only mean that this request or this message would be delivered here. You are expected to have something on this end which will read this content, do whatever I want it to do. It cannot respond back on the same channel because it's only one receiver. So you have to contact back through a back channel. So you need to have two ports, one for me to send the request, one for me to receive the results back, right? And you need to have something here which is processing this stuff, and that would be threads and tasks, and that's how the mark system is built, right? You have a notion of threads and tasks. So if you think this is a task, this is a task, you have to have multiple threads, and you have to implement this stuff and then get the results back. And that's how you build the mark kernel, right? Any services I want. So when they say I request a service, essentially create the message for the request, send it on the port, right? And then you get the result back on the other end. And all these mechanisms are asynchronous. What does that mean? All this request response is asynchronous.
So it's not blocking, it just sends the message.
Yeah, so it's not blocking, right? So when I send this request, I'm guaranteed that it will go to the other end, right? But it's not guaranteed anything else, right? So when you write this program here, you cannot, so if you're reading a block, you don't say read, wait for the result. So you send a request that I want this block to be read, set it over here. After some time, after some unbounded amount of time, you will get a response on the other port, right? They cannot guarantee how long it will take for you to get the response back, and that's a good thing or bad thing depending on your perspective. And in a lot of sense, it's good because you don't have to wait for the stuff, but it also complicates your program. So now you have to figure out when you're getting messages, you have to figure out what this message was for. So if I make a request to you, I have to know when I get a response back, I need to know what was sent and what was received, right? So those are the stuff that they built around it. So they built entire mark kernel based on the notion of threads and processes and this notion of interprocess communication, right? So the way you would, in the earlier lectures when we talked about kernel boundary here, and you have a application and you have some server, right? They all communicate using this mechanism. So you need to create a port, so you can send a request to the kernel, and the kernel may send a request to port. So you have lots of ports and messages within mark, and that's the only way that these things communicate, right? So that's the deal. The nice thing is it doesn't say anything about where these ports have to be. The ports are within the concept of mark, have a name, and you can access the name from anywhere, right? Which means that this can be on machine 1, this can be on machine 2, and this can be on machine 3, right? The port names have no concept of user identifiable name, so they can potentially have these ports and all the servers in anywhere they want. So to build a distributed system or build a single uniprocessor system, from a user perspective, the difference is not much, right? I can build a distributed system or a single process system is the same. Essentially, nobody cares where these things have to be. I mean, somebody has to figure out where these servers have to run. But from your application perspective, you don't know where they are. All you know is you make a request, you get the response back, right? And that's the reason why mark is supposed to scale to a large number, because why would this approach lead to scaling to a large number of nodes? Yeah.
You can access memory and files whenever you want on the machine.
Yeah, you can increase the number of these things, right? I mean, there's nothing which prevents you from figuring out how many servers or how many nodes this has to run. Essentially, as long as you can communicate with any of them, you're fine, right? But if you add the notion of asynchronous and this notion of distributed, what this means is this time becomes harder and harder to bound, right? So if I'm running on the same machine, these are two cores of the same machine, the time it takes for me to go and come back may be something. But on the other hand, if this happens to be in the US, this happens to be in India, this happens to be in like Europe or something, then the time for you to get the services can be quite large, and there's nothing you can do about it, right? The other stuff is the kernel will enforce certain privileges. So only people who have capabilities can communicate with each other, right? The capabilities cannot be forged, and capabilities are safe. Let's assume that they're safe, right? But what it does not say is anything about the intent of those stuff, right? So it does not say anything about how malicious they are or what have you, right? It does not say anything about the trust model. So if you're building a file server, all this means is whatever request you make, the kernel will pass it along to the right server. But this application can do whatever it wants to destroy the system. And I think they mentioned it a little bit on the towards the end, right? So this client may not respond back as soon as possible, may ignore some requests, and there's nothing you can do about the system, right? So you have to kind of trust the stuff. So the security model that they provide is any message sent by you will go to the right server, and whatever server sends will be sent back to you. But the correctness is not guaranteed, and these nodes don't have to respond back, which means that even good node or bad node, you end up having to allocate extra buffers and stuff because these nodes may not respond back in time. So you need to have something to respond back to them. So if you look at one of the overheads that they have to allocate extra buffers just so that if somebody sends a request, they can respond back to it, right? So it's not as efficient in terms of resource usage, but that's the price you pay because you want this ability to spread these things around, right? Does that make sense? So actually, those things were not introduced in this paper. Those things they introduced them as a sort of a tutorial kind of stuff, but those things were part of Mark for a while before this paper was written, right? So what they were trying to do in this paper was showing that using these primitives, using these interprocess communication primitives, they can implement a memory system. They can implement a distributed memory system, which may be a distributed virtual memory, which may be a distributed file system, which may be distributed something. They can build any sort of memory storage system using just these communication primitives, right? So the system itself does not support a notion of memory sharing, but they can implement memory sharing through these communication primitives. Does that make sense? So the idea here is, suppose you have two applications, right? In a traditional sense, you may create a notion of a shared memory, right? And these two may want to operate on those memory, right? They kind of share the same objects and they modify those stuff, right? It could be a file, or it could be a memory block. The way you implement that is you call the kernel. Both of these applications call the kernel, and the kernel works with another service called data manager, right? So you work with this to make sure that whatever you're trying to do can be achieved, right? The sharing of these two memory actually happens via the data manager, and that's what they explained. But essentially, whatever you modify here is transformed into a message, which is sent over the port messages through the kernel. The kernel mediates them, so they implement shared memory as messages, right? And so the paper essentially talks about how they can implement messages using shared memory, right? Does that make sense? So the context of this work is on how people build hardware. How many of you taken a course in architecture, multiprocessor, designing multiprocessor kind of systems? So for people who take it, very few, and I'm guessing most of you will take it in the spring semester, right? So one of the things that the hardware folks deal with is the same model, right? So if you're building a distributed shared memory system, right? If you consider, let's say you have 4 processors, right? And you want to build a shared memory system, which is sort of what we use. So this machine, which has 2 cores, is a shared memory system. But we don't think of it as a distributed shared memory system because the architecture is fairly simple. But let's assume you have a lot of processors. You have like a 4 processor. And you want to build a shared memory system, meaning all of them will see one shared memory, right? So if you have threads running on each of them, they're able to modify each of them, right? So one way to build this in the hardware would be to have this big shared memory, right, where all of them have access to them. So if this one wants to modify it, it modifies the location. This one can modify. This one can modify. This one can modify, right? So you can build it like this, where there's one memory, and then you have all these buses coming into that memory, right? So for folks who took architecture, or for in general, what would be the problem with this approach? I'm sorry, it's kind of like the. So you have, as you add processors, what happens?
Actually, the device gets exponential.
Yeah, this overhead becomes larger, right? So in the architecture, you'll see what happens with buses and all those things. You can't just draw lines like this in hardware. What you end up doing is you have shared buses. I mean, for cost and stuff. So you'll have one shared bus that this one connects to, and then you have all this stuff connecting to this one, right? And the bus becomes a bottleneck, right? So you can't draw lines directly into memory. It all has to go through one or fewer buses. So the design becomes complicated and complicated as you add more processors. In general, you can't go too far with this approach because at the end, the bus dominates everything else, right? So everybody has to go to the bus, and this dominates, right? So what you do is you like to distribute it. This is again in the hardware sense. This is not what we're talking about here. So what you do is you try to have memory as part of each processor, right? Then your goal is somehow to connect this memory amongst each other or to a global memory here, right? So the architecture folks basically try to have local memory, which sort of acts like cache. You have to have a mechanism to be able to read the other person's memory, and you still want to do this stuff. So essentially what happens is, if these two want to share some stuff, you have to decide where to place this memory, right? So it could be placed here, could be placed here, placed here. It could be placed on, so this is a third place. This is closer to one, or this is closer to the other. So whenever somebody modifies it, something in the hardware detects that something is being modified and then notifies the other part, right? So the design you tend to do on the architecture is sort of what they're doing here, which is you don't actually have a shared memory anywhere. You have something which is kind of distributed around the system, and whenever something gets modified here, you send a message across to the other part, and if the message channel is fast enough, then you get fairly decent performance, right? And this is also called a NUMA architecture because it's non-uniform memory access. Because if you have to access through a third party, things are slower. But if you have to access it directly from on your local machine, things are faster, right? So you have non-uniform memory access, and this is sort of how you build any kind of scalable machines. And I think when they talk about the paper, they say uniform memory access, which is what we looked at in the first case, is the norm, right? Which used to be the norm back then, but you can't build more than, I think 64 is sort of like the biggest you can go, right? 64 itself is like fairly big, right? But this one, you can go to thousands of processors if you want. Of course, it becomes more complicated because you have all these buses and stuff going around the system, but essentially this is how you scale the system, right? So in the model here, at the hardware level, you have no application semantics, right? So if the system, you tell the system that these two memory locations are kind of mapped to the same location, anytime something happens, you have to send the update to the other one, right? So when you look at the hardware perspective, you use the same kind of stuff. You send messages across these different memory locations to keep them consistent. But you have no knowledge of what is going on, so you don't know which ones have to be sent, which one doesn't have to be sent. You have different schemes, right? So for example, I cannot be lazy about it unless I have some hardware to support it, right? So for example, if I'm modifying my location really fast, and you want access to it, right? I don't know if I should send you all my updates all the time or do it lazy fashion or what have you, right? Because in the hardware, you don't have much of a control of what happens. The nice thing about this work is, in some sense, they're building this architecture in software, right? Where the kernel knows when the things have to be flushed, when the things have to be consistent. So only at those points does anything happen, right? So if you use this model in software to build sort of what you're building here, right? Only at the calls that you happen to have, you call the stuff, right? That's sort of what they're trying to do. They're trying to build a distributed system in software using messages, which is sort of what the hardware. I think the timeline might have been they were at similar times, or one preceded the other one. But the idea here is now you're trying to build something like this. You're trying to build a distributed storage system, distributed memory system, distributed anything, and you're doing that by using this stuff. You'll see how they're doing it in this paper. But essentially, the goal is you're trying. So the idea here is if two people are sharing, right? I don't try to maintain consistency of the memory on both the stuff. I let you have a local copy, right? I let the Mark kernel in your machine have a local copy. I let the Mark kernel in your machine have a local copy. I define at which points do they make sure that they are both the same, which point they invalidate. So I get you should get good performance and you can get all the flexibility, right? And unfortunately, I don't think the paper actually talks about it in that fashion at all. The paper is pretty disappointing for me because it's never clear what they're trying to say, right? Which is kind of surprising that no one felt like that, because they go into detail about the calls and like the port mechanism and all the function calls and the arguments and stuff, which are good as a tutorial or something, right? Many of you are not interested in writing a program for Mark. So it's not that important to know what the calls are, what the function is, but they don't actually say, this is what we are trying to achieve, this is what we could do with this stuff. I mean, it's kind of there, you have to like tease it out, but they don't say, this is what we are trying to solve, and this is what we solved, right? Does that make sense? This is a very disappointing paper because I think it's an excellent paper, but I'll put it this way. If you wrote this paper, it'll go nowhere, right? They got accepted, I think, because it's Mark folks and people know that they have a history, so they know that something good is happening, and you're supposed to tease it out of them. But it's unfortunate. I mean, they should have made it a little bit more clearer so we know what's going on, right? So this is excellent stuff, and I think the ideas that they use here is used in modern. So one of the things about computer systems is there are buzzwords which come into play at different points in time, and you kind of change what was being called at some point, right? At some point it was called network of workstations, and at some point it was called distributed systems, and at some point it's called grid, and at some point it's called whatever, right? So for people who come into the field later, grid computing seems like something which came out of the blue, or network of workstation came out of the blue, and then it kind of died kind of thing. But underlying all those stuff, it's the same thing, right? You are trying to figure out how to collect a bunch of systems and try to do something. And these are the foundations of how you would do that, right? So if you look at distributed systems or grids or clusters or whatever, your idea here is you want to have all this memory and all those things, and some programmatic way where I can access the services, access the resources from different machines, where I don't have to worry about where things are. I don't have to worry about whether the memory is local or what have you. The system has complete flexibility in moving things around, and I get the services I want, right? So it's very relevant these days, except it gets diluted by the fact that we call things differently. So it looks like this is something that was done, and then we kind of forgot and moved on to different kind of systems. But no, this is still as relevant as what they were back in the days. And I don't think the authors quite understood, if I were to read their mind, how far they can go with that, right? They said that this is running on 200 machines within a CMU, which is a big number back then. But the potential of running this on a cluster of 1,000 machines sharing the same kind of memory is really fantastic, right? But the paper was really hard to read, I thought, because it's kind of hard to figure out what is it that they had too many details, right? They're talking about virtual memory. They had a section on virtual memory system that they implemented on Mark, which sounded like a vanilla kind of stuff. I mean, it didn't sound like virtual memory is not invented by them. It's been around for a long time, so it was not a big deal, right? Then they talk about the facilities with the ports and messages. You can send very large messages through the port mechanism. In fact, I can send the whole my virtual memory as one single message, right? Which is nice, but doesn't change what you're trying to do. I mean, the size of the messages is not the important stuff, right? And there are still issues that this won't resolve, right? One of the issues is if I'm collaborating with multiple machines and my virtual memory is bigger than your virtual memory, and how do you solve that, right? So if my virtual memory happens to be 4 gigabyte and yours is 2 gigabyte, and be mapping and working on the same stuff, I don't think there's any way, right? I mean, we can only collaborate on 2 gigabyte because that's all you can collaborate, and that's that here. So even though they wanted it to be machine independent and be able to scale to a large number of stuff, you're kind of going to the lowest common denominator across the different machines. That makes sense, right? So if you have 2 machines and if your virtual memory is 2 gigabyte and mine is 4 gigabyte, we can only collaborate on 2 gigabyte.
At a time.
As long as your hardware allows something else for you to play, right?
Well, I mean, if for the first 5 minutes we start talking about your first 2 gigabytes, and then for the second 5 minutes we start talking about your second 2 gigabytes, I mean, that seems reasonable.
As long as you have some kind of hardware support, right? So the way that they're operating on is a memory. If you're operating as a memory, right? So if I create a 4 gigabyte array and I have pointers or something, right? I'm saying it depends on. Does that make sense, right? So if I create a large structure and I have pointers like this, right? You can never work with me because your address space can only deal with this much. So these pointers you can't see, right? And so, but there's nothing you can do to solve those, right? I mean, that's a basic fundamental hardware limitation. So even though you want it to be operating across multiple different machines, there are some hardware limitations which cannot be overcome, and that's nothing specific to here. I mean, that's inherent to these kind of systems, right? Right. So tasks and threads are what they were in other machines, other systems. So they add the notion of ports and messages, right? Ports are different from your typical networking protocol like ports and stuff because these are inherent to the Mark kernel. They have no notion of IP or what have you. Each port has a name, right? And the name is not something that it's internally created. So you have to know this name, and the name you know through your capability, and the capability you know because somebody gives it to you, right? So you can't look up a port. You have to be given a port by somebody. The kernel can say, this is a port that you can use to communicate with somebody. You can't make up a port, right? So in the Mark kernel, you cannot just talk to somebody unless somebody tells you talk to somebody and they give you a capability, which is also the port handle, right? So unless I get a port handle, I can't talk to somebody, right? Which is how it differs from networking kind of protocols where I can talk to somebody. I can find out where www.google.com is. Whereas here, somebody has to say, here is a handle, use this to talk to something, and that happens to be google.com or something, right? And those are sent through ports and messages. So when you start up, you have to establish a port with your kernel, and the kernel uses that to send you more capabilities to talk to other people. And port and capability are synonymous. You can have any number of senders and only one receiver. The key part is there's only one receiver. So you need to have 2 ports for two-way communication, right? It's a fixed length header and variable length, and the size can be as big as possible. They have a limit, which you would expect. I mean, you can't send infinite amount of stuff. So the number of messages you can send is bounded. You can increase it or what have you. So what they were trying to achieve with the system is be able to build a unified memory storage kind of system, right? So they're providing a notion of memory object management, where it's the model that I mentioned before, right? You have your application process. Everything goes to the microkernel mark, right? So you establish a two-way connection with it, right? You have to have a server with the data manager server or what have you, and you establish a connection with it. So their model is, once you do this, essentially you map virtually something over here into your address space, right? So all they provide is, through this mechanism, you can map something into your virtual address space through the kernel, right? So what you're trying to do is you map something from here into here into here, right? And they're providing, using these communication primitives, how you operate essentially on something here, right? So I want to operate on something which is on the server by using buffers inside the kernel, using buffers that are mapped from the kernel into my space. And the kernel's job is to make sure that whatever you do gets propagated over here, and this server can do whatever with it. This server can dump it into a storage system. If it dumps into the storage system, it's a file system, right? So the way you implement file system is you figure out what are the blocks that are part of this file, which is up to this file server, right? And all you do is you map the whole file as a memory map file concept in the application. You write into this file as you do memory, and whatever you do will get propagated through the kernel and at certain points that they define and gets flushed to the disk, right? So if you wanted to change a file system call from open, write, read, and close, essentially what happens, so this is what you write. They have a library here which translates that into this primitives. So essentially when you do open, it finds the right server to open the file, map that file into your address space here. Your write system call essentially becomes go to that offset and modify the bytes over here. Your read means go to the particular offset and read the particular bytes. And your close means at this point flush everything back to the disk, whichever policy that you use. And when you try to write something, if it is not there, you get a violation, a page fault kind of stuff. And the kernel at that point asks the server, what should I do? They are trying to read something which I don't have. And it's up to this server. This server implements a policy which states that if you try to write into this particular stuff, what should happen, right? Should the user get an error, or should I read something from here and send it on, right? So all the kernel does is it manages this mapping, right? Anything, if you try to do this as a virtual memory system, if you try to modify something, and if the kernel does not have the stuff, it has to ask the server, right? And the server and the application server and the kernel interact with each other to provide a wide variety of services, right? If it's a file system, this is what it does, and if it's a memory system, if it's a shared memory system. So some of the primitives that they define will help you do this stuff. But essentially, once you do that, so when I'm operating on a file, right, essentially what that means is somehow they get read, moved to the stuff here, and it might have been mapped here. So essentially you have one single copy here. So anytime I make a modification here, it goes up here. And then eventually it gets flushed into the disk, right? So when you build a file system using this primitive, things will be very fast because the semantics that you're implementing may be a little bit looser. It's basically a memory map file, right? And you can use this to build a large distributed shared memory, because essentially this one has to figure out where that particular memory is. So it could be on another system or server. You can talk to another server, get the memory, and pass it on to you. So the infrastructure basically says, application tells the kernel that I want to use this particular object manager, right? It's in the next slide. So this application says, I want this particular object manager. Or this particular application says, I want to use a file server, or I want to use a memory server, or what have you. And basically the kernel asks this one, I want to map this big chunk of stuff. I want you to tell me what should go in there, what content should be read or written, right? If I don't have it, I'll ask you. Otherwise, I cache everything. The user operates on this stuff, and you kind of keep pushing the stuff, right? So all of them gets translated into these messages back and forth, and messages really mean that you have to have some kind of a event handler here. So every time a message comes here, somebody here processes it, and then do whatever is necessary, and then send the response back. So when you modify something, it may lead to messages being sent here, somebody processing it, and then sending something here, processing it, and then sending back. Is that clear? I think I have one more graph which may make it more clearer, right? So they have so in the paper they go through the different system calls that each of this use, right? So from the application to the kernel interface, there's only one thing, which is VM allocate with pager, which means that to use this memory system, I have to say I want to allocate this much of virtual memory space, because everything gets mapped into virtual memory from the application perspective, including files or shared memory or what have you. But I have to say what the pager is, and pager is this server construct. So it's up to the application to say I want to use this particular pager, right? If this pager happens to be a file server, then you're using a file system. If it happens to be something else, what have you, right? So the kernel will use that knowledge to know who is it who's providing the service for you, right? So between these two, right, is where most of the action happens, right? So the kernel all the kernel says is, I'm going to map this virtual memory that you asked for. I'm going to manage it in the sense that if this content was given to me from here, right, I can let this one access it the way it wanted. So if it's given as read only, then if this one wants to read it, it can have read access. If this read write, then if this one wants to write it, it can write it. If you want to access something which hasn't been defined what it is, then I have to ask this one, and whatever it tells me is what I tell the user, right? And that's why you need these stuff. So pager init basically tells it establishes this stuff with the application server. So the kernel can ask for data. It can say, I want this particular page because the user mapped this memory, and now they're trying to access this stuff, right? This stuff I don't have, so you tell me what I should do. So it makes a request for data, or you can make a request to write data, flush data back to the server. So it needs those two, and it needs the unlock one. We'll see. This is basically for shared access. So if you have two people modifying shared content, so after your write is done, you want to say unlock, so other people can modify this content on the server, right? So the only things you need from the kernel to the data manager is be able to say, I want to initialize, I want to create this mapping, I want to be able to read and write the contents, and unlock. So I can. So when my write is over, I can send unlock so other people can modify this particular construct, right? From here, from the data server to the kernel, you need certain primitives to ensure consistency, and we'll see more of consistency when you go to the file system stuff. Basically, what that means is you are creating a local copy here, right? So if you're using a shared memory, so if two kernels are modifying the same location, this one has to be able to call back and say, I gave you something that you can read before, I want to invalidate it, right? And that's essentially what this thing is trying to do. So essentially this lets the server now call back into the kernel and say, I gave you something a little bit back as read or write or what have you. Now I want you to flush it, right? If I don't do that, then essentially you create an inconsistent system where another shared application here may be modifying the same location, and you may be still reading the old content because it's not flushed, right? The way it works regularly is this one drives it. You make a request for read or write. This one tells the kernel asks this data manager, right? And if now nothing is happening here, nothing happens in the kernel, nothing happens on this side. But you can't do that all the time, because if somebody else may be sharing this content and doing something. So if something else happens, this one knows about it. So it has to tell the kernel, whatever you're doing, you have to You have to clean the cache, flush the cache, or what have you. And these are used by different systems. So depending on whether it's a file system or database system or whatever, they need this mechanism to call back, right? And using all the systems, you can actually build anything you want. And they show 3 different systems, right? What do you think of the complexity of this system? I don't know if I helped by my explanation, but everything is asynchronous here, right? Which means that when I send a request, I don't know when I should get the response back, right? Which means the kernel can do a lot of stuff. So this can have any number of applications here. So it can send any number of requests to any number of people, and it can sort of proceed, right?
It would be pretty awful, because if you send a message to flush the cache, or the cache is inconsistent and you have multiple, and you're trying to access the same area, well, how long would you wait before you allow another client to write, or when you do?
Did that make sense? Let me draw a simpler graph, right? Or more complicated graph. So actually, let's say this is kernel, this is kernel, this is kernel 2, this is kernel 1, right? Your application here, which is talking here, right? And you have a data manager here. No, there's no reason why it should be 2. It could be any number you want, right? So this one has something mapped over here, and you have like a local cache here, and this one has some local cache, which are really operating on this particular stuff, right? So virtually there is this shared memory stuff which is being mapped into both the stuff. So if this kernel sees something that you're reading, it'll ask this and then whatever. If you write something, you'll have to tell it at some point, and then these two are talking, right? So they're talking, right? So one of the problem is, if you modify this, right, that may mean that this one, of course, would know about it. Means that this will have to say, you have to flush this area because somebody's modified it. So I can't let you use the old data, right? Which may be a policy that you implement for whatever you're trying to do, right? But since these all are asynchronous, when you say I'm writing something here write some content, there is no guarantee on how long it takes for a message to go from here till it gets acted on, right? It may be physical because these things happen to be wide area, or it could be because this is doing something else, right? And there's nothing which says this one has to do it in a certain amount of time, and that's one of the key things, right? It could be malicious. The data manager may not want to talk to you because it's just, I don't know. Or it could just be overwhelmed, right? So this may take a while for it to do, and which may mean that this flushing may take a while to happen. The systems that you build cannot depend on real time, right? So it cannot depend on, so we will see when you go to the file systems how you can address this using logical clocks and stuff like that. But in real time, right, you have no way of knowing how long it will take before things get flushed, right? You basically send the stuff to here, they send a request over here, and at some point, this will send a response back. At some point, you'll get the stuff back. So if you're operating on some of those things, they could potentially take a long time. Yeah.
I don't see it as particularly efficient, but based on what we read, I don't know if it was last time or 2 times ago, when they were talking about the logical clocks and being able to do things in the order that they happen in real time, it seems like you could overcome it using that kind of system. It just would be very, very, very slow.
So we haven't read that paper, right? The logical clock stuff, right? So logical clock is what all these things are really built on, right? Which means that you can only do causality, not the real-time clock, right? When they talk about real-time clocks in real systems, they're basically logical clocks where you keep sending messages often to keep the logical clock in sync with the real-time clock, right? So you cannot use real-time clock. Real-time clock can only be built by having messages sent to make the logical clock similar to the real-time clock, right? Which is what they say in the paper, which is a sort of a bogus argument, because that essentially assumes that there is another mechanism which keeps sending packets over here, another channel which keeps sending packets every so often to keep these things synchronous. So yes, that will work, but if this cannot answer for some reason, those will not go through either, right? So in the logical clock sense, this is not a problem, right? You don't need that real-time clock to make this happen. Logical clock sense, it will happen in the logical order. Unless this is malicious and not responding, unless this is malicious and not responding fast enough, they'll happen when they'll happen, right? The crux of logical clock basically is it'll happen in the order that, where events are happening. You should not let this move forward. It may take an hour, right? But you'll do the right thing because it'll come back to you. But in terms of real usable systems, right, it may be annoying to not have a bound. But that's nothing specific to this particular approach. I mean, that's distributed systems for you. And that's one of the things you have to deal with, where all you can guarantee is the causality order. But building the systems may or may not be trivial, right? And I don't think they kind of give they don't have much experience on how these things work. I think they implemented few of this stuff. And it's a very complicated system. And that's one of the stuff that you realize that when you go into distributed systems are a lot more complex to build because you have to worry about things are not as simple as a single processor system. We don't have to worry about these kind of delays and things like that, right? The flexibility of saying that these things can be on any different node, on any different capabilities and what have you. The direct cost is the complication, right? But hey, that's distributed systems for you, right? And they don't make it any particularly slow or fast, right? But the nice thing is it inherently builds this notion of a caches, right? So if you don't do this complicated stuff with other processors and stuff, if it's just a single process, right, the kernel can pretty much manage everything, right? So in the case of a file server, somebody has to, so if you write a POSIX like open, write, and close, right, somebody has to build a library which transforms that into Mark's model, which is essentially using the VM allocate and these mechanisms, which means that I can map this file into here. I can do any number of writes here, any number of close. This library can choose to only do some sort of a flush this stuff back to the, actually not even flush. I mean, like leave this stuff on this machine all the time, right? You don't have to call this data write at all, right? This application can only do data write before it does a close, right? You can do whatever you want, which means that all this file, the file I/O, will essentially happen on the local memory and will only get flushed when you do the close time, right? Is that a good idea? Yeah.
It depends.
Yeah, it depends, right? So what does it depend on?
If there are multiple people who are using that file.
Yeah, so consistency becomes a problem, right? If you leave all the caches around, multiple people operate on it, it's a consistent problem. What's the other problem?
If the other people are using it, then the latency is going to be unbearable because you're going to have to wait until the first person's done with the file before you can actually use it.
So that will lead us to the file system stuff we'll see in the next section, right? And that's essentially the crux of the problem, right? How do you get good performance while still letting these things be normal? So that's essentially the things you will worry about file system kind of stuff. The other problem is safety, right? If there's nobody else, right? What this means is I can keep this file open for days and hours and stuff. So I'm leaving the when these things should be returned at some point, right? At whenever the thing is, right? So the policy on when to flush the stuff is sort of here kind of thing, right? To get good performance, you should not flush anything to a disk, but that may be unsafe, right? So when they talk about performance in the paper, right, the only thing they talk about is if you do like a small file compilation, the thing is like super fast, right? If you read they have very little performance evaluation, right? And the performance evaluation said, well, this is like fantastic. I mean, this goes really fast, right? For compiling small files, this is fantastic, right? But that's essentially what I think what is happening, right? To get the best performance for the system, I never flush anything, right? So that means that if you're running a C compiler, once you open the file, I map everything into local memory, and it's in local memory. And if I have enough memory, then nothing ever gets flashed. And they say it's a small file. So you have a small file. I create a small file. I create these things. Everything is cached, and I get excellent performance, which is very unfair to say that, right? Because
What's the point?
what's the point, right? I mean, so this is like saying when you go to the file system, we will look at it, but actually we won't look at this stuff, right? Memory map files, right? A file system, right? So some of you who do the file system test, right? If you compare your file system with the RAM file system, that's really bogus, right? Because RAM file system is not really a file system. I mean, nothing ever gets returned to the disk, right? So you should get the best performance, right? So if you say ZFS is slower than RAM file system, duh, right? But that's not the point, right? So even here, they get 10 times performance because it's not a file system anymore, right? Unless you are able to guarantee that you're going to give the same consistency as other system, which means that you have to flush this stuff often, which means that this system can at best be as good as the previous system, or could be worse, right? Because you have more complexity, right? So it's awful to compare yourself with another system where there is no reason why you should be faster, right? But I don't think the good thing about the system is the speed, right? The good thing about the system is it's the flexibility, right? So essentially I kind of move so the kernel has very little to do. All it has to do is to maintain this paging. Anything illegal happens, it has to talk to this one, right? It's not defined what this should do, right? This could be a file system, it could be a distributed memory manager, whatever you can think of, right? And the argument is this is simple to build. This is not very complicated, right? Do you believe that? Do you believe that this will be simple?
The architecture that they built?
No, not architecture.
On top of the architecture.
The manager, the logic which goes into the manager.
Well, they did it. They did it.
Yeah. Should
So
is it simple? Should it be simple? It doesn't matter.
it's a one-time cost.
Yeah. I don't think it has to be simple, right? I think that the main thing is you are able to do whatever you want with it, right? I don't think it's important whether that's easy, right? If I can use this to build a file system, if I can use this to build a new memory manager, if I use this to do the copy on reference mechanism to do process migration, right? The idea here is, one of the things that you do in distributed system is you want to be able to propagate, you want to be able to migrate processes, right? So you want to be able to move a process which is running on this machine to another machine so that you can shut off this machine or what have you, right? Or move the process around. One of the challenges is you need to save the state of this machine here. You need to restore it back here, which means that you need to save all the virtual memory state and move it across, right? And that's painfully slow. So what you like to do here is you sort of leave so if a process migrates from node A to node B to node C, right? And if the process had this much state, when you go here, right? One approach is to move everything over here so that this is completely lost. But the approach that the lazy approach you can do is you leave the stuff here, and if you reference something here, then you bring it over here, right? And in the future, if it gets moved over here, then if something is not here, you kind of follow the chain. So you kind of do it in a lazy fashion, right? And you can build it on top of this, but essentially building the appropriate data manager for the stuff, right? So I don't think the key is the data manager is simple to write. I think the key is the data manager you can write such a data manager. You don't have to, in a regular Unix kind of system, you cannot extend the system to do that kind of functionality. Because all the extension for the functionality of the system is basically into the data manager, right? So the key strength of this approach is not that data manager can be written easily, which may or may not happen. The key strength is now I can do that. Now I can extend the system to do whatever I want, because all this system knows is one single concept, which is virtual memory mapping, right? Now all the system knows is that virtual memory, whether you have the object in or not, and what kind of privileges you have, whether you have read, write, whatever privileges. And And all this needs to know is what to do about the stuff. So it does most of the mechanisms. Some mechanisms are still left here, right? And there are some things you can't do. They can't change the page size to be whatever you want. It has to be a page size. The restrictions you expect. I mean, this is still going to the virtual memory